In this lesson, proximity measures for nominal, binary, and numeric data, we will cover various measures of data proximity, including categorical, binary, and numeric data. We will start with defining terms like similarity, dissimilarity, and proximity. After that, we will study measures or functions that operate on different data types, like nominal, binary, and numeric. At the end, we will look at techniques for standardizing data. In the knowledge discovery in databases, or KDD process, proximity measures play important role in the selection process. In other words, the data needs to be pre-processed in order to apply data mining algorithms like clustering, classification, and pattern recognition. A similarity measure or a similarity function is a function that takes two objects and typically gives a value between 0 and 1. 0, no similarity, and 1 is completely similar. On the other hand, dissimilarity or distance measure takes two objects and says how far apart they are from each other. So the smaller the distance means they are more alike, and 0 distance means that they are the same. A more neutral term is proximity, which can mean either similarity or dissimilarity. Very often, we present multidimensional data points as a data matrix. In this example, we loaded the iris dataset, which consists of 150 data points, n equals to 150, and it has 4 dimensions, so L is 4. Now that we have the data inside a matrix, one thing we can do is compute the distances between the objects. And the distance can be symmetric, which means we're going to end up with a triangular distance matrix, or it can be asymmetric. How do we compute a proximity for categorical attributes? So categorical attributes are things like colors, professions, etc. And we are going to look at the number of matches and the total number of variables. So in the very simple method, the distance is going to be P, the total number of variables, minus the matches over P. And here's an example. X1 and X2 represent students, CS, Junior, Java, running, Math, Junior, MATLAB, and swimming. So there is only one match. So the distance is going to be 4 minus 1 over 4, which is 3 over 4. So these two objects doesn't seem to be similar. So 3 over 4 is closer to 1 than 0. So if they were identical, it's going to be a 0 distance. The other method is to basically create a contingency table for a pair of binary variables and keep scores about where their values agreed or disagreed. Let's walk through this example. Suppose X1 and X2 went to the grocery store. X1 bought bread and lemon, X2 bread, eggs, and milk. Now we're going to summarize this data as a contingency table. So here we have object I and here object J. 1 and 1 are the things they agreed on, which is the bread, and as you can see there's a 1 here. T, the things they both did not buy, which is the beans. As you can see there is 1 here. S, the things that object J bought but not object I, which is 2, and the R, as you can see, is 1. So the distance in this case is going to be the things they disagreed on, which is the R plus S over the total Q plus R plus S plus T. So what is the major problem with this distance measure? What is the major problem with this distance measure? feel free to pause the video and think about it. The problem is in a grocery store, we don't buy most things, which means T, the items that X1 and X2 did not buy, is going to be very, very large. So as a result, the denominator is going to be large. So the distance between any two objects is going to be very tiny no matter what we do. Now we will look at the distance or dissimilarity measure for asymmetric binary variables. And for those variables, the value of t is not going to be part of the measure. In other words, the things that x1 and x2 did not buy do not make them similar. So the distance measure is r plus s over q plus r plus s. The equivalent similarity version with the asymmetric binary variable is called the Jaccard coefficient. And I'm sure you started to get confused. So here we were talking about this similarity for asymmetric binary variables. Now we're talking about similarity, which is the Jaccard coefficient. And it's very intuitive. So it's Q, the things that the objects agreed on, over Q plus S plus R. And it has a very nice Venn diagram like explanation where the similarity measure or the Jaccard coefficient is the cardinality of the intersection over the cardinality of the union. In this example, we look at the similarity between multiple asymmetric binary variables. In this small dataset, we have 3 objects, Jack, Mary, and Jim, and a number of symptoms and tests. We are going to drop the gender because it's symmetric, but in the medical testing, the value of abnormal or positive has a higher weight than the negative or the normal. So that's why they are asymmetric. And one way to deal with multiple binary objects is to compute the dissimilarity between each pair, like Mary and Jack, Jim and Jack, Mary and Jim. Then we go ahead and compute the distances, and we can find out that Jack and Mary seems to be more similar because the distance is smaller, let's say, between Mary and Jim. Now, moving away from categorical and binary data and considering numerical attributes, which is more straightforward. In this example, there are 4 two-dimensional data points summarized by the data matrix. And here we have the distance or the dissimilarity matrix where we have the distances between each two objects. And we assume here that this distance metric is symmetric, which means we only need to fill up half of those entries. A class of measures broadly called the Minkowski distance measures, or the LP norms, computes the pth power of the absolute values of their differences summed up and then take the square root. Some popular p-values are 1, 2, and infinity, but p equals 2 is the most popular. Some properties here, no matter what the p-value we are using, the distance is going to be positive, symmetric, and satisfies the triangle inequality. And in general, any distance that satisfies these properties is called a metric, but in the same time, it's not necessary every distance measure to be a metric. In fact, there are some dissimilarity measures that violates one or more properties of those. Special cases of the Minkowski distance when p equals 1, the L1 norm, or the Manhattan distance, is we take the absolute difference across each dimension and sum up. In this example, let's say we're trying to find the distance between x1 and x2. So the absolute distance across the first dimension is 3, and the second dimension is 2, and this is how we got the 5. When p equals 2, the L2 norm or the Euclidean distance, we are going to take the difference across each dimension, square it, sum up these values, then take the square root. And in this example, we're trying to find the distance between x1 and x2. Applying the formula, we end up with 3.61. Another special case when p approaches infinity, sometimes called Lmax norm or L infinity norm, supermem distance. So solving this limit is going to produce the maximum difference across any dimension. And here's an example. We're trying to find the L infinity between x1 and x2. And as you can see, the maximum across this dimension is a 3, which is larger than 2, so it picked up 3. Finally, in this slide, we summarize all the special cases, and you can see the distance between x1 and x2 in L1, L2, and L infinity. Standardizing numeric data using the z-score is a very popular method for data normalization. And the key idea here, we want to be able to control the scale of the data. So by transforming the data to have mean of 0 and standard deviation of 1, by subtracting mu and dividing over sigma, now we have a value that expresses how far this value from the mean in standard deviation units. It's like this data is 2 standard deviations away from the mean, or 1, 1.5, 3, and so on. The standard deviation has this issue of amplifying outliers. So if this is an issue in the dataset, one alternative is to use the mean absolute deviation, MAD. So instead of squaring the differences, we are going to take the absolute value and compute the MAD and use it in the z-score instead of the standard deviation. In summary, we discussed similarity and dissimilarity measures for categorical, binary, and numeric data, and talked a little bit about standardizing numeric data.